So good morning, everyone. So this is my second talk, and they gave it back to back to me, and this is a little bit about my passion, and it's about tensegrity, a system that has been used from art into science and engineering. And this is basically, if you're familiar with art, you might have seen those sculptures out there. So these are sculptures by Kenneth Nelson, who passed away recently. And so Kenneth Nelson worked with cables and struts. He puts them together, he finds a stable equilibrium, and these struts float in the air. This is an interesting and intriguing concept for engineers. So directly when he did that, he was working with Buckminster Fuller. Buckminster Fuller is a well-known, I would say, architect, engineer, and he was a multi-dimensional personality. So he came up with the word tensegrity, tension and integrity, which then was used into multiple, let's say, other projects. So tensegrity has since gone from art into science, starting from mathematics. It went also from art directly to architecture. So architects have been proposing tensegrity structures due to their aesthetics. So you see here, this is the Blur building that was a temporary construction in a lake that looked like a cloud in the lake, but actually was, it had that, I would say, skeleton, which was a tensegrity structure. If the architects used it, we have to guarantee its stability, and engineers directly jumped in. Civil engineers saw that we can span we can have long spans. So this is a tensegrity roof, again in Switzerland. It's the World Cycling Center. It has a tensegrity roof, and it's a very interesting and aesthetically pleasing structure. So we have to guarantee the stability of this thing. But beyond that, it has been used in science. So Dr. Imberg, who visited our school a couple of years ago, if I'm not mistaken, has been using that for the modeling of the cell, the cytoskeletal mechanism, in order to simulate the combination of the mechanisms with respect to the structure of the cell. And of course, NASA jumped in also, because these are robust structures. So NASA presented this ball-bot, the super ball-bot, which is basically a tensegrity structure that they came up, which has actuators in the struts, so it can change the length of those elements, and by changing the length, we can make it move. So they proposed this design for planetary landing and exploration. So before we send anything to space or we put it in our buildings, we have to guarantee that it's stable, that it works, understand its performance, not only in the short term, in the long term, but also under damage. So this is what we are doing here. So we are focusing on the generative design, so how we can have these structures designed and get the desired properties that we want. So we want to control their shape, we want to control their behavior, and we want to also inform their assembly. Their assembly, although it looks elementary, it's a big problem, because typically the stability is not guaranteed unless you have all the elements in place. So what we're using, again, we use a little bit of math. So we use rigidity theory and graph theory, and we are inspired, like the previous talks, from nature. So we use the mechanisms of adhesion and cellular fusion. So we're putting things together, and they stay together as independent organisms, or they're fusion together. And by doing that, we can create complex structures. So this is basically the composition of the module that you see on the right. The module on the right is the one that NASA have been using. And this is the composition by different units, we call them cells, of that model. So what we're doing is we're adding cells and we're removing elements throughout. So throughout this process, our structure, which is on the left side, is always stable. So we don't need to have temporary supports or anything, and it can guarantee also taking some loads if needed. So we can compose that structure, and we can also understand the behavior of the structure on the right by understanding how it is composed from the structures on the left. So this is the end result. So this is pretty basic, but then when you're using a method, you have also to show that you can do interesting stuff and more complicated stuff. So we came up with a Stanford bunny, which is a benchmark problem in computer graphics. So we polygonized the bunny, and we did different resolutions, as we call them, of the tensegrity. So this is the class 1, so the bars are not touching, but we also did some other versions of it. So this is another low resolution version, and of course something that I will ask my students to build, the high resolution. Thank you.
Thank you.